gentlemen, and welcome to the second Astronomy and Astrophysics public lecture series of the 2012-2013 academic year. It is my great pleasure to introduce to you this evening a man that you should be very familiar with. It's Dr. Terry Oswalt. He is the head of the Physics and Space Sciences Department here at Florida Tech. He has been at Florida Tech
forever.
Since anybody can remember.
Since the glaciers retreated.
1958.
Yeah.
That's a good enough estimate for me. So I guess without further ado, I would hand it over to Dr. Oswalt.
Thank you. Let's see. Well, I have to say I really enjoyed preparing for this lecture, not because I'm the world's foremost authority on Pluto, but because I don't know, just a confluence of things happened. I was asked by the University of Alabama, Huntsville, Mike Brown's alma mater, to write a little bio sketch for their alumni magazine. And I thought, okay, fine, I know enough about planetary science to be dangerous. And then I got a call from MIT, a colleague at MIT, saying, Pluto's going to occult a star this month. And a number of the students in this room participated in observing that event a week ago. 2 weeks ago yesterday, and I'll tell you a little bit about that. And then, so it just seemed like the right thing to talk about right now. It's also the just past the 6th anniversary of Pluto's demotion as a planet. So I thought maybe people would be interested in not necessarily celebrating, but at least seeing a little bit of the history that happened in Prague, the Czech Republic, back in late August of 2006. So let me boot up our the other half of my presentation here, and I'll get started. Okay, it worked a minute ago. All right, let's get rid of the extra things that Bill Gates likes to put in there. I don't know how to get that off the bottom of the screen. Okay, all right, it just went away. The gist of my talk is kind of a direct ripoff of a book written by Michael Brown, who, as you will come to know tonight, is one of the leading experts on the outermost fringes of the solar system. And I've got a copy of his book up here, not for sale or anything, but How I Killed Pluto and Why It Had It Coming is a bestseller on the New York Times list. I don't know if anybody here has read it, but I had a hoot reading it. It was like, oh yeah, I remember that. Yeah, I remember that. But Michael wasn't even present at this meeting where Pluto was voted out. He was on vacation, I think it was off the island of Vancouver, with his newly born daughter Lila and relatively new wife at the time, celebrating the discovery of like half a dozen new planets, quote unquote, outside the orbit of Pluto. And he had a vested interest in wanting them to all be called planets because he would have been the first person to discover a planet in 70 years. 1930 was when Pluto. So despite the title of his book, he really would have preferred to have, at the time, Sedna and Quaoar and the half a dozen other objects that were discovered in the early to mid-2000s, right before the 2006 meeting. He would have loved to have been famous for being the first person in 70 years to find planets in the solar system. The fact that he named his book Why I Helped Kill Pluto is testament to his willingness to simply accept the fact that it's a new situation that we have to deal with in the solar system, that the solar system is enormously more complicated than we ever envisioned. And that's the way it is in every branch of science. Every once in a while, you just get an awakening experience. And this is one of the gentlemen, among about a dozen, who helped us achieve that awakening in the solar system. So let me give some perspective. For some of you, it may have been several years since you've looked at the solar system as a whole. So let's do a little bit of a background check. Here it is to scale the solar system. Now, obviously, the solar system doesn't have all these lines and colors in it, but the scale of the solar system is enormous. And that's not even a good start on the enormity of the rest of the universe, as you probably already could guess. But one of the things that strikes you the most about the solar system as a whole, two things in this diagram, plotted pretty much to scale, is how round all these orbits are. You can't even tell they're not quite circles, can you? They're not. They're ellipses, but they're pretty close to circles. And another thing that's striking is that the innermost 4 or 5 planets are pretty tightly knit to the sun, and the rest of them are kind of spread out and more or less equally spaced. And then another thing that looks, if you rotate at this in 3 dimensions, is, wow, how flat the solar system is. All the major planets are in the same plane. And Mars, okay, Mars is tipped just a smidge. Even Kepler discovered that Mars' orbit was a little peculiar back in the 15 and 1600s. But for the most part, the solar system is flat and planar, as we say, and pretty well set up with a tightly knit batch of planets on the inside where we are and a loosely knit batch of planets on the outside where we are. So there's some properties that just demand a scientist's attention. How come? That's a question that naturally comes up. There's yet another peculiarity or pattern in the solar system that my intro to space science students could point out too. And that is, although in this plot the planets aren't drawn to scale and distance, they're imaged to scale and size. And the inner planets that are close to the sun, those 4, Mercury, Venus, Earth, and Mars, are dramatically similar, and so are the 4 outer planets. The size is a striking tendency of difference. The inner 4 planets are much more obviously different. They're small and rocky and have little or no atmosphere. You might think we have a good atmosphere here, but it's thinner than the skin of an apple is to an apple. It's just a shred of an atmosphere compared to Jupiter and Saturn and Uranus and Neptune, which are mostly atmosphere. The so-called gas giants, the Jovian planets, the gas giants. And these are the terrestrial rocky planets with weak or little or no atmosphere. And so, okay, that's a pretty good classification scheme. Jovian, gas giants. Terrestrial, Earth-like, rocks, 3rd rock from the sun we live on. And scientists are getting pretty good at modeling how to make solar systems. Peter Bodenheimer is one of maybe a dozen theorists in solar system cosmogony, the origin and evolution of solar systems, planetary systems as a whole, not just ours. And he can build a model. In fact, here are some frames from an animation that extends over millions of years that show exactly how you could get a solar system like ours. Those are false color images for temperature, pressure, and composition and density, not actual pileup of matter, but it shows that when you start out with a cloud of gas and dust, and we see such clouds all over the sky, you've seen one without even knowing it if you've ever looked at the constellation Orion. If gravity is capable, we won't go into how that happens, that'll be another public lecture. If gravity is allowed to do its thing and pull a cloud together, then that cloud automatically gets flat and spins up faster the way an ice skater speeds up a spin when she pulls her arms in. She shouldn't do anything but pull her arms in and she speeds up. If you spin a pizza dough, it also flattens out. Fortunately, the ice skater doesn't because her body's stiff enough to resist that, but she would if she were Jell-O. You get flatter as she spins up. And Peter and others show mathematical models that indicate that planets that are within dust and gas that are within about 5 times the Earth's distance from the sun, that's Jupiter's distance from the sun, by the way, are close enough to the proto-sun that they get bombarded by the radiation that the proto-sun, when it turns on and begins to burn fuel, and the gas is evaporated and blown out into the outer solar system, and much of the gas and much of the dust is simply shoved away or evaporated or falls into the sun, leaving the inner solar system depleted in gases. That leaves a whole bunch of planetesimals, shards of material, dust grains that stick together, that have similar velocities, tend to jostle up and stick to one another, and eventually you end up with a bunch of rocky planetesimals, and that process continues and continues and continues until you've got big guys instead of little guys. Out in the outer place, out past the so-called ice line, where at Jupiter's distance and beyond, water can't be liquid or gas, it has to be frozen, it tends to be ice. Then out here, those ices and rocky material condense to form primarily gaseous planets, and it's gaseous at that time because the planets themselves are contracting and heating and making the ice melt, and you end up with gas giants. And it all fits very well and good together in the solar system models that Peter and others show, that we should have 2 classes of planets. gas giants, and terrestrial planets. And here's a nice little 3 frames from a long animation that show that you can throw these little objects about the size of this campus by the millions, just make planetesimals by the millions, throw them in there in their own unique orbits, and over less than 500 million years, about 10% the age of the solar system, you will end up with about the same number of planets we got. And the inner ones will be rocky and the outer ones will be gaseous by and large. So you can build solar systems. You don't always end up with 8 planets, but you build solar systems, they come up with a reasonably small number of planets based upon simple physics. The calculations are pretty complicated because there are lots of objects to keep track of, but the physics is rather simple. It's just a lot of calculations. So we think we understand why the solar system is the way it is, or we did until about 2002 to 2005 when things kind of got out of hand. In the middle of the most recent decade. One of the things that becomes pretty obvious in these models and was discovered a century or more before the models could prove it is there's a lot of leftover stuff when you build something. You know, if you've ever built a house, you know what they do after they're done. The builders put all the junk that's left over under the sod if they can get away with it. And there's a lot of building debris underneath your yard in case you've never dug it up and looked. That solar system is not an exception to that rule. And in fact, because Jupiter is so massive, its orbit out here essentially shepherds and prevents debris from getting out farther than its orbit. And the planets inside that distance between Mars and Jupiter are kind of shepherded, and there's no way that that material can actually get together and form a planet. So mathematically and theoretically, we understand that there's a bunch of leftover building debris between Mars and Jupiter because these 2 planets have prevented, through their gravitational perturbations, they prevented those planetesimals from getting together less violently than the others were able to, and so they're left over. What hasn't been swept up by Mars or Jupiter is now safely separated enough in the debris belt between Mars and Jupiter that we now call that the asteroid belt. Properly, it's called the minor planet belt because the word asteroid means star-like, and these obviously are not stars. And there are over 20,000 whose orbits are known so well that you could go out on any given night and find them in a telescope the size of ours, at least most of them. There are probably millions. But most of them are the size of a rock this size, the kind of meteorites you pick up every once in a while on the surface of the Earth, to house size, and those objects are all too small to be seen by earthbound telescopes. We can only see those if they're about the size of this campus or larger. The first one to be discovered, and hence the number 1, we're up to actually I think something like 50,000 now in tentatively identified objects, was discovered in the year New Year's 1801, New Year's, the first day of the new century, 1800s, by Giuseppe Piazzi, and within 5 years there were several more discovered between the orbit of Mars and Jupiter. Mars and Jupiter. And it didn't take very long before it was realized that there's a whole bunch of them out there, and that not one of them is the size of even the moon. The biggest one known so far is about the size of the Gulf of Mexico. 500 or so kilometers is the scale, about 900 kilometers across is the size, and this is the best picture we can take of it at the present time until the year 2015 when the Dawn spacecraft gets to Ceres and takes our first close-up pictures from orbit around it. It's clearly round, but that's the best picture we can get. You can see the individual pixels in the Space Telescope image here. It's so magnified. But you can see a hint of structure. There probably are ice packs on the surface. There may very well be frozen water on the surface of this mini planet, we'll call it. Minor planet is the right word. William Herschel's name is here because he was a contemporary of Piazzi, and he had discovered a bunch of other things, not the least of which was the planet Uranus, and was very famous in the United Kingdom for that alone, but a lot of other things to boot. He coined the word asteroid for this object because in a telescope it looks like a little point of light, just like a star, and oid means like, so asteroid means star-like. But clearly that's not a star, because stars don't have disks that you can see in a telescope. So, in fact, Florida Tech, in the distant past, like several decades ago, about 25 students participated in what is still today the best measurement of the size, shape, and density of the asteroid Ceres when it was predicted to pass in front of a distant star. You can imagine how many stars there are in the sky, countless numbers, and any one object is casting countless shadows from all of those stars in the sky, right? And every once in a while, a shadow has to pass through the Earth, like a little eclipse. And in this particular occasion, Ceres' shadow passed right through the Central Florida area. The top edge of the shadow was right through roughly Jacksonville, and the bottom edge went through the Caribbean. And we deployed students, and a couple of people from MIT came down, but most of these were our own students and faculty in teams of 2 or more at the FIT Observatory here in Melbourne, No Name Key in the Keys, and Great Exuma, and the Turks and Caicos Islands. I happened to be at that site right there at the time. And you can't even see the star that was going to be occulted. And you can't even see the Ceres with the naked eye, but in a telescope what you see is that a tiny little dimming of a few percent has to be measured electronically because the eye wouldn't notice such a little dimming. But the second that dim occurs is the second the leading edge of the asteroid's shadow has reached you. And you know how fast the asteroid is moving in kilometers per second. So the second that the star reappears, subtracted from the time that it disappeared, is a time interval. Velocity is distance divided by time, so those two allow you to calculate the distance across the face of the asteroid. And in fact, here's the 2 points that I was responsible for down in Providenciales. And the MIT crew that went a few miles south on Grand Turk Island observed nothing. That's what the dotted line means. They were below the predicted, they were in the predicted shadow, but the shadow's error was enough that they missed. Lucky for them, however, is they were also underneath a thunderstorm at the site. That's a NOAA weather satellite photo taken within 10 minutes of the occultation. And so they were the only team that missed the observation, but it was fine because they wouldn't have seen anything anyway. So Mother Nature was on our side, and all the blue points here are points that our students and faculty members took, and the white points are teams that went to Arizona and Mexico. And what really happens, if you could see it visually, this is a different occultation, is as the Earth turns, the stars draw trails in the sky, but this particular star was occulted by an asteroid you couldn't even see for about 11 seconds. And that tells you how big the asteroid is, even though you can't see it. It's the most accurate way, short of going there, of getting sizes and shapes and densities. And until the Dawn spacecraft gets to Ceres, this is the best measurement still of this asteroid. They come in all shapes and sizes. They literally look like building debris, don't they? We've been to several of them. The Galileo spacecraft on its way out to Jupiter, and practically every outer solar system shot that we've taken since then has been scheduled to pass by one or more of the previously unvisited ones. We even had the NEAR spacecraft, Near Earth Asteroid Rendezvous spacecraft, actually crash on Eros. Really wasn't a crash because you could run fast enough to put yourself in orbit. The gravity's so weak on a tiny thing like an asteroid. So it was more like a parking maneuver. There's no landing gear on the spacecraft, but it just sort of docked with the planet. And there is on the asteroid Eros, the Shoemaker spacecraft now, just sitting there as a little monument for one of you. This generation will be the ones that go out to mine some of these asteroids. I won't go into why they're really the place where the next gold rush will be, but Eros in particular is an Earth-crossing asteroid. It will hit the Earth someday, fortunately not soon, but it means you can go there really easily with a spacecraft for much less money and energy than it took to go to the moon and back, because there's no gravity to speak of. So this is what the building debris looks like in the asteroid belt. Rocky, airless, irregular in shape. Some of them even have moons. It's not unusual for an asteroid to have moons. That was a big surprise in the 70s and 80s when we were first exploring up close and personal. But this is about Pluto. So let's move out in the solar system, and it'll become clear why I talked about the asteroids in a few minutes, I hope. Pluto has a story that really begins at Neptune. These two people, an Englishman, John Couch Adams, and Urbain Le Verrier, no good blood between the English and French, especially back then, by the way, almost simultaneously computed the orbit of Uranus, which had been discovered several decades earlier, and found that its orbit was getting tweaked a little bit. There were errors in the computed orbit compared to how Uranus was actually moving. And they, using orbital mechanics, wasn't called that back then, it is now, some of these students will be taking that class soon, computed that there must be another planet out there that's tweaking Uranus's orbit, and they both independently predicted where it should be within about twice the diameter of the full moon. That's pretty good accuracy. And lo and behold, it was discovered almost exactly where they both predicted it. Now, Urbain was way more of a PR guy than John, and so he got the initial publicity, and it came out later that Adams really had probably preempted the prediction, but he failed to publish it in timely fashion. And in science, he who publishes gets the credit, not he who does it first, or she, as the case may be. Two he's in this case. And so this was considered to be what I would say the founding of orbital mechanics. The first instance where the laws of gravity were used to find something new, to discover something new by theoretical calculations. These calculations are the foundation of space missions today. We use the same equations to get to Mars and land rovers on the surface of Mars. We just use computers rather than logarithms, but it's the same calculation. And in this case, even in our telescope, Neptune won't look any different than that little postage stamp picture. A slight little disk, maybe if you've got good night vision, you'll catch a little greenish blue tone of color to it, but probably not. It'll look just barely like a little disk rather than a star. And if it happens to be the right time for its big inner moon Triton to be visible, you'll see it, unless it's behind the planet. So maybe if it's up tonight, I forgot to check, you can look at it with our telescope. But that's all Neptune looks like until the great Voyager missions toured the outer solar system in the mid to late 80s. Triton is worth mentioning in the context of Pluto also. I would bet that in 2015, when the New Horizons mission gets to Pluto, did you know there's a spacecraft on the way to Pluto right now? 2015, we'll see our first up-close and personal picture of Pluto. I'll bet it looks a lot like Triton. And it was a huge surprise that out here, 30 times farther away from the sun than we are, 30 astronomical units where Neptune is located, and Triton in orbit around it, we see volcanoes. Now, they aren't the kind of volcanoes that you'll see in Hawaii. These are cryovolcanoes, liquid nitrogen squirting up through the ice pack and forming the same kind of features that we see magma forming. The outer solar system is every bit as active, it turns out, as the inner solar system. It's just a whole different temperature regime with different things like liquid nitrogen, which in our atmosphere, if we were to move the Earth out there, it would be on the Earth. It would not be an atmosphere, it would be the crust. And whenever there's a place that's warm enough, that crust would rupture and the liquid nitrogen would squirt out in a geyser-like volcano, so-called cryovolcano. And what you're seeing right here are two that happen to have been recently erupted, and the wind has blown the debris downrange. And the entire equatorial band of this surface apparently has been completely coated by the material that's spit up by other volcanoes, cryovolcanoes. So pretty interesting stuff out in the outer solar system. That so-called cantaloupe terrain is now viewed as a signature of cryovolcanism. Extremely cold geologic activity. Every bit as violent as the kind of volcanoes we see here, just a lot colder. Okay, it wasn't too long after the discovery of Neptune that the next generation of astronomers started plotting Neptune's orbit and saying, oh, Neptune's orbit's a little bit screwy too. There must be something even farther out. And about that time, the 1890 to 1910 time frame, a gentleman from Massachusetts took his family wealth of the great Lowell family of Massachusetts, took his share of the wealth, and Percival Lowell went out to Flagstaff, Arizona, and the observatory he founded still exists today. They've been on the Discovery Channel, and big debut of the so-called Discovery Channel telescope at Lowell Observatory, the first research-grade world-class telescope built by a TV station. Pretty good stroke of genius, I would say. Built-in publicity and the money needed to build one of the world's best telescopes. Lowell himself would be very proud of that idea of the Discovery Channel telescope. He hired high school graduate Clyde Tombaugh, who bragged that he was a mule skinner by background, but I doubt that very much, to take over the search for Lowell's pet project at the time, finding Planet X, the next outer planet beyond Neptune. And that is more tedious than you can imagine, because you take a picture, and then a few hours later you take another picture, and then the next day you take these two pictures and put them side by side in a machine that has a microscope that allows you to look at a tiny little piece, one little star image at a time, and you blink back and forth, and if anything has jumped back and forth between the two images, it's moved in the sky. And that's how he found Pluto in 1930. You can imagine how tedious that is. It took several days to look at each plate, because you start at the top and you just work your way across, back and forth, back. I've done some of that. It is not easy work. I looked for asteroids when I was an undergraduate student using blink comparators like that. And Clyde was the one who discovered Pluto in 1930, and to his dying day in 2007, he considered it a planet, as did the rest of the world. It may be interesting to note that in 1930, Pluto got its name from an 11-year-old English girl named Venetia Burney. She's the one that suggested Pluto, and her uncle, father's brother would be uncle, happened to be the person, also an English librarian, who suggested the names of Mars' two moons, Phobos and Deimos. So I guess they've got a family tradition of naming new planets. It wasn't a formal competition as far as I can tell, but there was a lot of discussion in the media about what Clyde's new planet should be named, and the god of the underworld was the one that got the most traction in the media. So Venetia gets the credit for suggesting that. And by the way, if you're not, in case you don't know it, this guy got his name for the same reason. He was named Pluto in 1930, and Walt Disney, it was not an accident. Walt Disney knew a good publicity stunt when he saw one. So this is how Pluto got his name too, after the planet. So, now, things were pretty stable for decades and decades, but in the late 1970s, Jim Christie and Bob Harrington, who's still alive at the Naval Observatory, actually I think Bob Harrington died recently, but anyway, contemporary astronomers, were trying to upgrade the orbit of Pluto. In fact, their goal was to find out if Pluto would pass in front of any background stars so you could use the occultation method that I talked a bit about Ceres on, because it's so far away. That's one of the best ground-based pictures you could make with Pluto. And that's blown up so that you can actually see the little grains in the film. It's so magnified. And they noticed in these microscopic pictures of the photos taken over the years that the Naval Observatory had been observing that region of the sky, that sometimes Pluto had a bump on one side and sometimes it was on the other, but most of the time it didn't have a bump. Now most people would just say, oh, that's a Kodak star. That's what we call them, defects in the emulsion, a little flake of dust or a little fault in the development or a little manufacturing flaw. It's called the Kodak star, because Kodak made all these astronomical plates back then on special order. But Harrington and Christie noticed that the bump was there every 6 days or so, and flaws in photographs don't occur like clockwork. And so the discovery was that Pluto has a moon. Charon. Charon is sometimes how it's pronounced, but Christie's wife's name was Karen, K-E-R-E-N, so he insists on pronouncing the best bud of Pluto, the god of the underworld, not Charon, it's Charon, like his wife. So that's the way you should pronounce it. He named it, so the IAU approved it, so that's the way it is. The orbit of Pluto is peculiar for a bunch of reasons, and Pluto is peculiar for a whole bunch more than that even. First of all, its orbit looks nothing like the other planets we've talked about. There's the orbit of Neptune, nice circular orbit for all intents and purposes. The orbit of Pluto is wacko, elliptical, highly eccentric. In fact, for about 2 or 3 decades, 2 to be exact, 1979 and 1999, for 20 years out of its 250-year orbital period, it's actually closer to the Sun than Neptune, and it develops an atmosphere as all that solidified nitrogen and methane and other things that would be a gas in a normal atmosphere evaporates in the tropical summertime of Pluto's approach to the Sun, and it develops an atmosphere. And I'll show you that it does have an atmosphere in some observations we made a couple of weeks ago. The other thing worth noticing, well, is this little artist's picture that there's Charon, there's the Plutonian surface, if you will, and the Sun would be nothing more than a bright star in the sky. Next time the moon is full, go outside. Look around you. That's what the Earth would look like if it were as far away as Pluto from the Sun. So think of the Sun as no brighter than the full moon, 40 astronomical units away. 40 times the Earth's distance from the Sun means Pluto gets 1/1600th, 40 squared, less sunlight than we do. Again, we'd expect cryovolcanism to be an option out there, depending upon the exact mass and circumstances. And one of the things that's important to note, look at how massive Pluto is compared to the Earth, 0.2%. Now you remember that picture of the inner and outer solar system. Little planets called terrestrial planets, big planets called gas giants or Jovian planets, and now we've got one that's 0.2% of the little guy's masses. 0.2%, not 1%, even less than 1%. It's about 20% the size of the Earth. So you can do the calculation in your head and realize, well, Pluto's not rocky then. It must be something that's fluffier than rocks to be 20% the size, but 0.2% the mass. Ice, a snowball, if you will. Think of a snowball with a little bit of dirt in it, and you've got a pretty good idea of what Pluto must be like. Now, just a stroke of dumb luck, astronomers seem to have more than their fair of luck. Charon's orbit is perpendicular almost to its orbit. Pluto goes around the Sun like this in a whack-ass tilted orbit, all right, but the orbit of its moon is almost perpendicular to that. So its orbit, here's the plane of Pluto's orbit, and as we went through that period of time in the middle to late 1980s, Charon's orbit was almost directly in line with the Earth. We were seeing its orbit edge on, and what that means is eclipses occur. Charon was passing in front of and behind Pluto for several years. It won't do that again for another 250 years. Talk about dumb luck. We're just born in the time that Pluto was able to do that, once in 250 years. And when that happens, when eclipses are happening, you know that each little sliver of the surface of Pluto is being covered up sequentially and then uncovered sequentially. And if you observe many of those over and over and over again, you can work out how to put the pieces of the light that you've collected back together into a sort of a pseudo picture of what the surface of Pluto must look like to explain the way the light has been changing during those eclipses. Okay, the geometry is pretty complicated, but the basic idea is I could take a little slit here and look at one little piece of the room here, and then another one, and another one, another one, another one, and take all those photographs and put them together. You can take a shredded piece of paper and put them together into an image too, couldn't you? It's the same kind of idea of these eclipses. A little more geometrically complicated, but the same idea. And so this is our best reconstructed image of what Pluto looks like. That's the best one you can get right now. It has some light areas, it has some dark areas, so clearly there's some interesting geography to look at when we get there and see it up close in detail. Notice the peculiar orange color. Not what you'd expect for a snowball. But it is what you'd expect for hydrocarbons like methane and ammonia and other hydrocarbons that would normally be solid ice out at Pluto's distance, that some of which have evaporated and fallen down in rain on the surface when Pluto is balmy during its close approach to the sun. And the sun's ultraviolet light tends to turn such organic materials reddish brown in color. The way the headlights on your car turn that nasty shade of orangey, pearly color, same kind of damage, ultraviolet damage. Different chemicals, but same idea. High energy radiation causing chemical changes that cause differences in color. We'll know for sure what Pluto looks like when Alan Stern, the PI, the principal investigator on the New Horizons spacecraft, actually gets and flies by. It won't go into orbit. It'll fly by Pluto. It's an El Cheapo, by NASA's standards, spacecraft. And in order to put something in orbit, you have to have an enormously more expensive spacecraft with all the rockets and maneuverability, and every ounce adds hundreds of thousands of dollars more to because you're throwing it all the way to Pluto. That's a lot of energy, and energy is money in this business. So this is just going to be a flyby, but it'll give us our very first up close and personal, not simulated, but real images of Pluto in a couple of years. Using the largest ground-based telescopes and reanalyzing all of the data, this is the very best picture that I've found in the literature. It just came out a year or so ago, based on Hubble Space Telescope reconstruction of the surface of Pluto. And again, you see that reddish-orange color with lots of dark marks. You'd swear that was a blurry picture of Mars, if you didn't know better. So, a lot to look forward to. But we haven't gotten to the exciting stuff yet. We're getting there. One of our alums from our department, as a matter of fact, Max Muchler, will be here for homecoming in November. We're giving him the homecoming. He doesn't know it, so don't tell him. We're giving him the homecoming alumni award for the College of Science this year. He in 2006 co-discovered two new moons. There's Pluto and Charon in the Hubble spacecraft image. And lo and behold, there's two more, since named Nix and Hydra. And they're in orbit around the two in the same direction. And Max and Alan Stern was at the time the senior research support scientist for the Hubble Space Telescope. We have about 5, I think maybe 6 former FIT students from our department at the Space Telescope Science Institute. 2 were just hired last year by Max, as it turned out. Max is the guy you have to talk to if you get telescope time on Hubble. He's the one that programs the telescope. He's the one that downloads the data once it's collected, massages it, and cleans it up before you get it. At least he's one of 2 or 3 people that do that, but he's the senior member of the team. And he was doing the imaging for Alan Stern on Pluto to get Charon's orbit better established and to do the orbital calculation for Pluto itself, and noticed 2 objects that were in the field of view that had moved between exposures, and he calculated that they must be in orbit around Pluto to explain the motion. So he really is the one who discovered these 2 moons. And that was just a few years ago, coincidentally right before, a few months before Pluto was demoted as a planet. Just this year, 2 more moons have been discovered. And you might guess Max had a hand in that too. Yes, he did. But this one is a little more difficult. You had to completely block, or nearly completely block, the brilliant Pluto and Charon. That's what this black bar is. It's a big filter, a very dense filter strung across the image so that Pluto and Charon couldn't blind the detector. And there's Nix and Hydra standing out like a sore thumb, but voila, there's even Moon 4 and Moon 5. There may be even more moons there, so Pluto's got a mess of moons, 5 at least at this point in time. So things are way more interesting than little dots in the sky would have led us to believe back in 1930 when Pluto was discovered by Clyde. 2 weeks ago tomorrow, September 9th it was, the planetary science community, in particular a group at MIT, contacted us to say that Pluto was scheduled to pass in front of a nondescript background star. There it is, that whopping bright star is actually a star with Pluto on top of it from our telescope. That's a picture from our telescope. That's Pluto with a star behind it. Doesn't look like much, but the shadow of Pluto, as the Earth is moving faster in its orbit than Pluto. You can think of Pluto as just hanging there in space, and the Earth passes by it because it's got a faster orbital velocity. And that means the shadow of Pluto passes from east to west as the Earth passes through that shadow. And lo and behold, our telescope here in Central Florida was smack dab, or very close to, the middle of the predicted track. These three lines are the track, with the middle one being the middle of the track. And Charon was scheduled to pass right over South America, that shadow. And we have a telescope in Chile right there as well. That's our telescope in Chile at Cerro Tololo Inter-American Observatory. We remotely access that. But our colleagues at MIT used that telescope with our permission, of course. And we did the observations up here. So here's the ground track to a little bit more precision, and that Pluto-Charon occultation, as it's called, last week. The raw data for the whole set looks like this, and it's pretty darn obvious that something happened early on in that time we were watching. If you just blow up this part, just this part where the interesting thing happened, this is what the data looks like, and basically Pluto had covered up the star for a little bit less than 5 minutes, 274 seconds. It's pretty easy to do the math on this. Orbital mechanics say that Pluto's shadow was traveling at a little bit more than 5.5 kilometers per second during that time. 5.5 kilometers per second times that many seconds gives you a distance of about 1,500 kilometers across the face of Pluto. That's about 1.5 times the size of the Gulf of Mexico, or about 50% larger than Ceres. So even this data here, as raw as it is, we haven't finished reducing it, there are other things we can get out of it, says that Pluto is tiny. Pluto is like an asteroid in size. It's like Ceres in size, except it's not like Ceres in composition. Ceres is a rock. Pluto's a snowball. These are some of the Dr. Batcheldor took this picture of the students hovering around waiting for Pluto to disappear. It didn't disappear. You couldn't even tell with the eye that anything happened. You had to measure it. The other thing that's clear from this is if Pluto didn't have an atmosphere, the light would just abruptly cut off, like a knife edge cutting off the starlight, and then it would just come back. You remember that photograph I showed where the star trail had a notch in it? The light just cut off and then come back. That's what an airless body does. Well, this didn't just cut straight off and then come straight back, did it? There's an atmosphere there. There's some atmosphere on the Earth, and there's some atmosphere on Pluto that caused that effect. But mostly it's Pluto's atmosphere. So, as cold as it is, it's balmy right now because Pluto is still as close to the sun as it ever gets. And so it's got an atmosphere that will snow out and turn into a sheet of ice in a few decades when it moves away from the sun. Now let's get to Michael Brown's interest in Pluto. We're running short of time, as I always do. There is no end of articles in the literature. One of the more recent ones is right here from just this year that predict there are probably could be bodies as big as Jupiter in the outermost solar system. Not likely, but possible. In fact, the limits are that out beyond the orbit of Neptune at 150 to 250 AU, that's the Earth's distance, 1 AU, 150 to 250 times farther from the sun than the Earth is, there could be objects like Pluto that are as big as Mars that haven't been detected yet. We can't rule them out. It's worth looking for stuff like that. They're so faint, they're really difficult to detect with our current technology. There could be even stuff out there up to 4 times Jupiter's mass, as long as it's several thousand times as far away from the sun as we are. And if you think those are big distances, the nearest star to us is over 250,000 times farther away than the Sun and the Earth are apart. So 250,000 is roughly the nearest star, and so a tiny fraction of the way to the nearest star, there still could be big planets. So back in the late 1990s and early 2000s, this team of three, Michael gets a lot of press because he's a really good speaker and writer, but he hired a postdoc, Chad Trujillo from the University of Hawaii. Michael is at Caltech. And later on, he teamed up with a colleague, David Rabinowitz, at Yale. And they used the grand old 48-inch Schmidt at Palomar Observatory that's mapped the sky several times over the years, but equipped it with the best detector available at the time and did an automated search of the entire path of the sky that most people would call the zodiac, but in astronomy it's called the ecliptic. It's where the plane of the solar system is, out to an unprecedented faintness level. And it didn't take them long to start finding objects past Pluto, past Neptune, so-called TransNeptunian Objects, TNOs. We like abbreviations in science. TNOs, TransNeptunian Objects, is the technical name for anything like Pluto. Pluto is a TransNeptunian object. And they have found a whole smorgasbord. Here's how they do it. They have the computer take several consecutive images. Can you see the object in here that's moved slowly? Right up here. See it? That's Sedna, if I remember right. Actually, no, I take that back. That was initially named Xena, you know, after the Warrior Princess TV show, and her sidekick, Gabriella. The IAU didn't like that name very much, so they made him rename it, and the name he suggested was Eris with the moon. Turns out it has a moon. When it was imaged with the Space Telescope, they found that even it has a moon. And they named that one Dysnomia. Those of you that might know your mythology will recognize that Eris is the goddess of discord. She's the one that made things, caused a fight that ultimately caused the Trojan War. You remember that story? And the sub-goddess Dysnomia is the goddess of lawlessness. So we've got the goddess of discord and the goddess of lawlessness out there. And this, the IAU really liked, because you will not believe how much fighting the discovery of this object and all the ones after it caused amongst the scientific community. It's a very appropriate name, the god of discord and the god of lawlessness, as I hope I will impart to you. Here's the spectrum of, this was its license plate number in the computer jargon of the time, but it's Eris now. Pluto's spectrum is in red here. It's bright enough you can get a pretty good spectrum. Eris is so faint you can't sample but big swatches of its spectrum. So these big dots are the places where the spectrum or brightness of Eris is bright or dark, bright, dark, dark, bright, 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 bright. And in Pluto's spectrum, these dips here and here and here and here, 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 and even out here are all due to methane ice. When the sunlight bounces off of methane ice, it subtracts out certain wavelengths and causes darkenings in the spectrum. And Pluto has methane ice on its surface. Its atmosphere is not an atmosphere for the most part. It's frozen pancake ice on the surface, methane, with a little smidge of an atmosphere now. And this high point and this darkening and this darkening and the approximate agreement over here, although the color's a little different, Eris is more reflective in the optical wavelength and therefore appears brighter than Pluto for its distance, or it wouldn't have been discovered at all. It reflects better than Pluto, or it wouldn't have been discovered at all. Suggests that Eris has methane ice on its surface too. That its atmosphere is sphere. It's a surface. Here's your little smorgasbord of the top, the big ones, the ones that are comparable to Pluto in size. Each one of them has an interesting story. I have nowhere near the time to tell them. They're all interesting. There's Eris and Dysnomia. There is Pluto with Charon, Nix, Hydra, and the two others that have just been discovered. Makemake was discovered right before Easter, so it was originally named the Easter Bunny by Mike and his Trujillo and Rabinowitz crew. It has a peculiar reddening color. Haumea has a really interesting story, and it was discovered to have two moons, and it's spinning so fast it's egg-shaped. And a bunch of other TransNeptunian objects have been found in other places around its orbit, suggesting that it's spinning so rapidly that it must have been whacked big time in the past, and the other objects in that orbit are shards from that collision, and these two moons are probably leftover pieces that didn't have escape velocity. So even collisions occur out in the solar system beyond Pluto. And Sedna was called the Flying Dutchman because its orbit makes Pluto's look tiny in comparison. It's called the Flying Dutchman because it never could be seen twice. It's at the hairy edge of detectability, so in some of the pictures it was present, and other pictures it wasn't. It was like a ghost coming and going. Probably depended on which side was rotated in your direction, and if it was just barely reflected enough to be seen. Sedna's orbit is extremely large. It is probably the first of a new class of objects. These others are almost all standard TransNeptunian objects whose proper name stems from Gerard Kuiper, famous planetary astronomer from the 50s, 60s, who predicted on the basis of studying comet orbits that the solar system must be surrounded out to about 150 times the Earth's distance from the Sun, out to about 150 astronomical units by a debris band that makes the asteroid belt look tiny in comparison. This debris band isn't rocks like the asteroid belt. It's snowballs like Pluto. And it was Kuiper, actually properly pronounced Kuiper in the Dutch pronunciation, it was Kuiper who predicted that there must be a band of stuff out there even though he couldn't see it. But it was people like Michael Brown who began to discover some of these so-called Kuiper belt objects. So instead of calling them TNOs, it's probably better to now call them Kuiper belt objects, KBOs, to sort of remember who thought of the idea first, Gerard Kuiper. And so we now have building materials left over from the formation of the solar system beyond Neptune. There's another belt out there. And other stars have them too. I could show you 20 or 30 pictures like this. This is one of the better ones. I happen to be collaborating with Paul on a book right now. Paul was the first person to image one of the brighter stars in the sky. Foma Lauda is up in the Fall constellation over around Pegasus, not in Pegasus, but it's in that general piece of the sky. It's a naked eye star, you can see. And with the Space Telescope and the Keck telescopes, he managed to put an occulting disk in front of the star to block the glare from the light. You can see the arm that holds the little occulting disk so that the star's brightness is dimmed by many, many, many orders of magnitude. The dot has only been painted in there to show you where the star was located. And the light around that star has both the shape and color to match those objects that you were seeing in Mike's menagerie of TransNeptunian objects, reddish, orange in color. But more importantly, there's the orbit of Neptune to scale. Foma Lauda is a similar star to that of the Sun. And look, there's a Kuiper belt around outside the orbit of Neptune and another star. We're seeing it from the outside rather than from the inside. More interesting. If you remember that little headline of a paper I showed you a minute ago, right here in that little box, so tiny you probably can't even see it unless you're in the front row, but blown up for your entertainment here in this bigger box, are two exposures of this same type, same object taken a couple of years apart. Look, there's an object that's moved. That's an object that has to be way bigger than Pluto or it wouldn't be visible. And it's way, way farther away than Pluto is from its parent star. So there probably are big objects around the Sun out there that we can't see yet. The reason we can see these is because we're outside. We're outside and we can see the collective reflectivity of the whole menagerie. And if we're lucky, maybe one or two. This was the first time a planet's been directly imaged in the Kuiper belt of another star system. Now, to put things in perspective, Sedna is a special beast. I told you it makes Pluto's orbit look teeny in comparison. Well, here's the Kuiper belt put in perspective. Here's the inner solar system. We got your Jupiter. We got your debris band called the asteroid belt and the terrestrial planets. Okay, jump out. There's the next step out. There's Jupiter's orbit. Now it's tiny. Saturn, Neptune, Uranus, and Pluto. And you can see how out of round Pluto's orbit is. There's Sedna, its discovery position. About twice as far from the Sun as Pluto, but that ain't it. We wouldn't have discovered Sedna at all. Mike's team wouldn't have discovered Sedna at all if it hadn't been on the near side of its orbit, because its actual orbit jumped down to here. There's Pluto's orbit right there. There's Sedna, the same place in the diagram. There's Sedna's orbit. Makes Pluto's orbit look like Mercury's orbit in comparison, doesn't it? The implication is that there's more to the solar system than even the Kuiper belt. There's beyond the Kuiper belt, a fellow by another Dutchman, I don't know why the Dutch are so big on outer solar systems, but named Jan Oort, predicted that although the Kuiper belt is in the plane of the solar system, farther out, maybe even halfway to the nearest star, maybe hundreds of thousands, 100,000 astronomical units out and into roughly overlap with the Kuiper belt, is a spherical arrangement of debris that was blown out in all directions or never had a chance to fall in during the solar system's creation. Think of a dandelion gone to seed. The sun is in the middle, and all these objects, little snowballs, and by the trillions, by the way, are in the Oort cloud out at this scale, which makes even Sedna's orbit look tiny. And the nearest star on this scale would be over in Orlando, by the way. So we're not talking about anywhere close to being to another star yet. This is the inner Oort cloud. And we think that one of the working hypotheses is that Sedna is an object, a renegade from the innermost region of the Oort cloud. Like Pluto, seems to be the innermost, first discovered member of the Kuiper belt. So, Jan Oort and Gerard Kuiper, although they have been dead for a number of years, have a good legacy in greatly expanding our solar system, what we believe our solar system is like. And there's only one object now, Sedna, that seems to be, I forgot, here's Jan Oort. He died at the ripe old age of 93. Here are the first, so at about 2006, just before the International Astronomical Union, oh man, I'm running behind schedule. I'm sorry about that. I hope I've saved the best to last, unfortunately. Jan Oort, these two people went pretty much head to head and so did the rest of the scientific community. Alan Stern, you might call the planet, the Pluto hugger. And since the 1990s, Brian Marston has wanted to declare Pluto not a planet. He, in fact, wanted to give it a number, the number 10,000 in the asteroid numbering scheme. He reserved a nice round number for it, just on the off chance that he'd get to rename it. Brian has been in charge of the Minor Planet Center for decades. He's only recently retired. But these two people basically represented two kinds of the division in the planetary sciences. The ones that feel on domination or dynamical grounds that only the big eight count, because they're the ones that determine the structure and they fling everything else around. They're dominant. They dominate everything so-called dynamically. On the other hand, there are people in the scientific and planetary community in particular that says gravity ought to be more important in determining the shape of an object, and anything that's round ought to be called a planet. And Pluto and Ceres are both big enough to be round. If it's rocky and about 250 miles in diameter is enough to make gravity make it round. And if you're icy and low density like Pluto, about 500 kilometers, about 500 miles, is big enough to be round. And if you were to take that route, you're going to have lots of planets. If you're going to take this route, domination, only 8 planets. So those are the battle lines drawn in 2006. Which is which? At that time, we had going on 50 objects in the Kuiper belt and one candidate for the Oort cloud to consider. So, what is a planet? Okay. By the way, this picture is taken from the daily newspaper of the IAU. Every day for the 2-week period of the IAU meeting, you get a little newspaper and what happened in the previous day and a cartoon. If you read it, it says, "Ladies and gentlemen, we have to complete the definition of a planet soon. The sun is turning into a red giant." That's a long time in the future, but in 2004, the planetary science community convened a meeting to try to decide what a planet definition should be, and they couldn't come to an agreement. Those two lines were drawn, and they just couldn't come together. In 2005, they tried to do it with a smaller committee and still went nothing. It's like the NFL coaches and referees, or owners and referees. They just couldn't find an agreement. And so they did a dirty deed, in my opinion. They brought this to unsuspecting attendees of the IAU General Assembly in 2006 and basically popped the question to the whole assembly. You guys decide. We can't make up our mind. They didn't say that, but that's how it came out. You guys decide. You have a copy of the ballot that I cast on that date. So I'm going to ask you to, and here's in fact one of the drafts, and here's Jocelyn Bell up there at the podium talking about, or actually that's not her, I have another picture of her in a minute, talking about one of the drafts of what the planet definition is going to be, and the Florida Today newspaper ran this editorial ad at about the time this was all going on. And every time you walked out of the assembly building, which had maybe room for 500 or 600 people in it, you'd be swamped by reporters. I was with, this is Sylvia Catalan, who was a graduate student from Spain at the time, and I had been talking to her about the research we were thinking about doing. She was just finishing her dissertation, and the reporters come up to us and start asking us about Pluto, and I said, Sylvia can handle that, so why don't you talk to her? She enjoyed that. So I took her picture dealing with, I think it was a European equivalent of CNN. Anyway, here's what that particular vote was, and yours truly sitting in the second row right there. You know, one of my friends took the picture just to prove that I was there. Because we didn't realize it was going to be controversial, but anytime you see people wandering around with TV cameras, you know something's going on. The question hadn't been popped yet. But, and these are cartoons from the daily IAU newspapers. The original designation of Eris was this, UB313, so to Pluto B or not UB313. A lousy takeoff on Shakespeare, but here's the vote being cast, and I was taking the picture while I was holding my, my thing up. So let me ask you to replicate this based upon what I've told you about the solar system. I'm not taking sides. You already know how it went down. You've got your ballot. And I'll give you the details in a minute if you want to hang around long enough, but I just wanted to cut to the chase, so to speak. This is a smaller group than the 500 or so people that voted, but how many of you have been convinced that Pluto is not a planet? Raise your vote. Okay, you want to count it? How many of you think Pluto should be a planet? Raise your vote. That's a fairly mixed crowd. More voted Pluto out, though. It was pretty obvious. In this particular vote, there was almost nobody raising their hand on the issue of Pluto not being a planet. It was almost unanimous. It was so close to unanimous they didn't even bother to count the vote. But what we did reject, and here it is, here's the actual ballot that was voted. Resolution 5A, there's 423 who bothered to vote. There might have been a few that were just standing there and taking pictures and whatnot. A planet is a celestial body that's in an orbit around the sun. It has a sufficient mass for itself. I'll let you read it. It's a definition of a planet. A dwarf planet is an orbit around the sun, has sufficient gravity for it to be round. That's what hydrostatic equilibrium is. But it hasn't cleared the neighborhood around its orbit. And it isn't a satellite. So that means Charon's not a planet, and neither is Pluto. Okay? It's round, but it's not dominating that region. It's just part of the Kuiper belt, the way Ceres is part of the asteroid belt. Now, if Alan Stern was here, he would use a few curse words, first of all. He would say, yeah, but what's the difference between a lake and an ocean? Where do you draw that line? Is Australia a continent or an island? Is Greenland a continent or an island? Is Europe a continent? Wait a minute, Asia's fastened onto it. Geologists don't seem to be all up in arms about the definition of a continent or an ocean. Why should we be all up in arms about the definition of a planet? It's a generic term that doesn't demand, this is Alan speaking, that doesn't demand nitpicking divisions. Okay, so that's a valid argument too. I can see that. What we voted down was, okay, in fact, let me do what Jocelyn Bell did. Can you turn the lights on, Dan? Oh, there it is. No wonder I couldn't find it. This is exactly what Jocelyn Bell, the chair of the session, did. Yeah, you probably don't know where I'm going with this, do you? So here we got this. There's Pluto. Okay, let me put it right here, and hopefully it'll stay up. I didn't check to see the table was big enough before I came over. So maybe you can hold the umbrella so it won't fall over. Just however that works. Okay, what do we have under here? Resolution 5B says, Resolution 5A says Pluto's not a planet. Rattles a lot of cages when you say that. It also says a whole bunch of other things aren't planets either. In explaining what Resolution 5B means, Jocelyn brought out this gear, not the exact stuff, but the same thing, same idea. Pluto, planet Pluto. Planets like Jupiter and the Earth, although this is more like Jupiter because it's gaseous. Okay? And Ceres, the mythological goddess of harvest and grain. And if you vote this resolution, those are round objects. They're also planets, but they're called dwarf planets, but they're not, and that means they're really planets. Okay? They're dwarf planets, and they're really planets. That's what the umbrella means. We put it all together, and this is a dwarf planet, and this is a dwarf planet, but this is a planet, a classical planet, and to use another adjective that was used at the time. Okay, you can take that down now. The umbrella is 5B. It says now, Pluto's actually a planet, even though it's a dwarf planet. You see that fine distinction? It's a planet. Now it's a dwarf, 5B was turned down because we all, most of us, the majority of us, felt that, okay, if you're going to be nitpicking about saying what's a planet and what's not a planet, let us not go backwards and now include a few things that were leftovers that got left out. The umbrella is not needed, in other words. So once you've said dwarf planet is another term, then stop saying that it's the same as a planet. Why invent a new term if you're going to say it means the same thing? So that's why it got rejected. And this last one here is basically the recognition that dwarf planet is a different category altogether. Take the umbrella away, so to speak. So that's how it went down. And the votes are there for anybody to see. You can tell that the first one was pretty near unanimous. The others were a little closer. We all hated the word dwarf, but it was better than some of the other obnoxious names that had been put forward. And I won't go into that. So let me stop right now because I know some of you are anxious to get to see through the telescope. Pluto's up right now. If you want to see a little dot in the telescope, you'll have to use the camera. One thing that's explicitly omitted from this is, wait a minute, there are over 1,000 planets now known outside the solar system. Or wait a minute, are they planets? Or are they dwarf planets? Or Plutinos? Or Plutoids? Or TNOs? I can't tell you. Nobody's decided yet. We put that off. And it's been on the back burner for 6 years now. I don't know when it's going to be on the front burner. But we've learned a lesson in generating controversy. I think it'll be on the back burner for a long time. Because how are you going to tell whether that little dot that moved in Paul Callas's picture of Foma Lauda is dominating its orbit, or if it's round or not? How are you going to decide? You can't. It's a whole realm that we can't address, a level of detail we can't address at this time. I've already said this. I've already said this in so many words, but there it is in more plain English. And then Pluto sitting over there saying, I can't believe I'm sitting at the little planets table now. So anyway, I'll stop right now with this slide and say, well, actually I got one more slide I'll just leave in the background for the questions and answers. That paradigm shift, yes, shift happens. And it happened to us in 2006. And now we have to face the facts that we're in an expanding era of knowledge, and the terminology that we've been using, planets, minor planets, etc., is outdated. But at this point, we don't know how to expand it properly because we don't have but one possible Oort comet, Oort cloud object, and only something like, I think we have 300 or 400 now, Kuiper belt objects. And none of them are close enough or have been imaged well enough to really see whether they should be further divided. Maybe there's even more classes. And to a scientist, that's great. That means there's job security, right? Right? We're not upset about that at all. The fact that we can't come to grips over nomenclature means we're on the cutting edge. That's what it means. That's a good thing, not a bad thing in science. So, whether I've convinced you or not, I did vote the way the ballots went on all those votes. I voted exactly the way everybody else had voted, and I felt and still do feel that way. But whichever way you feel, it's a good time to be a planetary scientist because the inner solar system is just the tip of the iceberg. There is so much more out there in our own solar system, you wouldn't believe it. In the next decade, I think we're going to find some wonderful surprises out beyond Neptune. We just, Mike would probably say if he was standing here, you just ain't seen nothing yet. And Mike is doing right now the deepest possible search to find more Oort cloud objects. That's his goal for the next 10 years, is to find more than one, because he thinks they're all out there, and that's what he's doing right now. If you're interested in this sort of thing, these aren't for sale, they're not freebies, they're just display copies, for my own personal copies, but those are some of the books that are pretty good reading on the Pluto story. I particularly like Mike's. But if you've got a grade school kid, that's a good one. That's for grade school kids. I got a copy of it up here. It's pretty cool. And last but not least, I told some of you that I actually got some hate mail when the announcement for this lecture came out. And here's a couple of the more interesting ones. I'll leave that in the background, and I'll quit right now and ask if you, in the interest of equal times, you can read their complaints about Pluto and its lack of being a planet. How people in Michigan and New York found out about our local talk, I don't know. They really must have nothing else to do. But anyway, thank you for coming. I really appreciate the opportunity to share with you my story. Just remember, no umbrella for Pluto.
All right, thank you, Dr. Oswalt. In the interest of time, let's have two questions, so you better make them good and short. Two questions. No? Yeah.
Would it have been more valuable to wait for the horizons to actually get some information?
I got to come back here because I'm a little hard of hearing.
With Pluto having an atmosphere, isn't that more of a, I don't know, consideration for its planet?
Well, it might be. The fact is Pluto's atmosphere freezes out for 90% of its orbital period, and we just happen to have discovered it while it's close enough to have a little bit of an atmosphere. That's why we want to see more occultations in the next 10 years or so. The more the better, because we want to watch that atmosphere settle out.
Do you see yourself laying it down and bringing Pluto back as a planet? Isn't the horizon?
I don't know. Probably not. I think what we'll find is an object like Triton, and Triton is not a planet by the definition that's been accepted. I will say we'll probably see that Pluto is way more active than we ever thought it would be. That there is stuff going on the surface.
Question? Or was that technically two questions? I think it was two questions. Okay, let's thank
That was two questions, yeah.